Space Shuttle 6 was the second operational mission and Flight 1 for Challenger, this country's newest spacecraft.
The spacecraft looks much like its sister orbiter, Columbia. The two are about the same size, but Challenger's lighter, stronger construction, together with its more powerful engines, enabled the new orbiter to carry more than 15,000 additional pounds of payload.
Many weight-saving improvements had been made. The orbiter itself was almost 2,500 pounds lighter because of structural changes. The external tank weighed 10,000 pounds less than the one used on Shuttle Flight 1. The solid rocket boosters were almost 4,000 pounds lighter. The three main engines were upgraded to 104% of rated thrust. A blanket-like thermal material replaced 600 thermal tiles in non-critical areas, and all 30,000 tiles were densified to improve their durability. This stack could carry over 17,000 pounds more into orbit than Columbia. On Shuttle Flight 6, Challenger's cargo, the Tracking and Data Relay Satellite, TDRS, and its solid propellant inertial upper stage rocket, the IUS, weighed almost 19 tons. TDRS is launched from the payload bay by ejection springs, released when explosive bolts are fired. After Shuttle moves a safe distance away, the first stage of the IUS rocket fires to boost the satellite from 150 miles to 22,300 miles in altitude. Then the first stage separates. Shortly thereafter, the second stage of the IUS rocket fires to circularize the satellite's orbit. Solar panels and antennas are deployed to provide power and tracking and data relay capability. Having attained a circularized altitude of 22,300 miles and traveling at the same speed as the Earth's rotation, the satellite will remain fixed in orbit over the same location continuously. Later, the first TDRS will be joined by two more identical satellites. The three will form a space communications network, providing almost continuous coverage to Earth-orbiting spacecraft, not the 15% ground stations provide. The network will be able to track 26 Earth-orbiting spacecraft simultaneously. And because TDRS satellites only relay data, they do not process it, 20 times more information will be handled by this network than could be by ground stations. All data will be relayed directly to the primary NASA ground terminal, White Sands, New Mexico, and from there via domestic satellite to other NASA centers. America's first spacewalk in 9 years.
The thing we wanted to test and evaluate there was our ability to do construction type work, repair type work in the environment of the shuttle orbiter. We wanted to check out our suits and the life support systems on the back that we call EMUs. We wanted to evaluate how we check them out before we take them into the airlock and depress and take them outside. We did have 3 suits on board. We wanted to look at our ability to move about in the payload bay, up and down the longerons or up and down the long distance of the payload bay, and across the bulkheads fore and aft. We wanted to look at our safety tether dynamics, the safety tether we wear to be sure that we stay connected to the orbiter. We wanted to exercise various tools, winches, and in summary, our basic ability to do work, constructive type work or repair type work in the environment of the orbiter.
Commander Paul J. Weitz, who is the leader of this mission, has been an astronaut with NASA since 1966. And he served as a pilot on Skylab 2, the first manned Skylab mission, spending approximately a month in orbit. He was born in Erie, Pennsylvania, and has degrees both from Pennsylvania State University and the U.S. Naval Postgraduate School. Carol Bobko joined the NASA's astronaut corps back in 1969 and was a crew member of the highly successful Skylab Medical Experiments altitude test. This was a 56-day simulation of the Skylab mission, enabling crewmen to collect medical experiments baseline data and evaluate equipment. He also was a support astronaut for the Apollo-Soyuz test project and served as a lead astronaut in the test and checkout group at the Kennedy Space Center on the first flight of Space Shuttle. Carol Bobko is considered by the people at the Kennedy Space Center to be an honorary member of Kennedy. Mission Specialist Donald Peterson is a retired colonel of the Air Force. He's also a graduate of the U.S. States Military Academy at West Point and has a master's degree in nuclear engineering from the Air Force Institute of Technology. Peterson joined NASA back in 1969 and served on the astronaut support crew for Apollo 16. His main areas of responsibility within NASA have included engineering support, man-machine interface, and safety assessment. Dr. Story Musgrave is a medical doctor in addition to having degrees in mathematics and statistics, business administration, and computer programming, chemistry, physiology, and biophysics. He was selected as a scientist astronaut by NASA back in 1967 and worked on the design and development of the Skylab program. He was the backup science pilot for the first Skylab mission and was a capsule communicator for the second and third missions. Dr. Musgrave participated in the design and development of all of the Space Shuttle extravehicular activity equipment. During his period with NASA, he has also kept up his clinical and scientific training as a part-time surgeon at Denver General Hospital. He's an accomplished parachutist and has made over 300 free falls, including 100 experimental free fall descents involved in the study of human aerodynamics.
This is Kennedy Space Center. The view we're now observing on the television is not a fairyland scene, but is actually Pad 39A and the Space Shuttle Challenger. Challenger was rolled out of the vehicle assembly building this morning about 4:19 a.m. Eastern Time and is now moving the 3.5 miles to the launch pad. Dense ground fog today is making the scene a little bit surrealistic, but beautiful nonetheless. The orbiter Challenger, its external fuel tank and solid rocket boosters are just barely poking out of the fog this morning, but is rolling about 1 mile an hour to the launch pad. The trip takes about 6 to 7 hours. Challenger should be at the launch pad about 10 a.m. Eastern Time this morning and should be hard down on its launching posts about noon. Workers will immediately begin connecting the orbiter to ground connections, both mechanical, pneumatic, fluid, and electrical, and then we'll begin checking out the orbiter in preparation for its first launch in late January. This is Kennedy Space Center. The orbiter Challenger on its crawler transporter is now moving the final few feet into position over the launch support posts on top of the launch pad. We can see the crawler moving at its slow speed, the 14 million pound load or so being carried by the crawler transporter. And within an hour or an hour and a half from now, we'll have a mated condition on top of the launch pad where the crawler transporter deposits the mobile launch platform, whose bottom we can now see on the screen, onto mating positions on top of 6 support posts on the pad. The final few feet are very delicate because the positioning has to be very precise, and it's almost impossible to jockey the platform around once it's nearly in position. This is Kennedy Space Center. The orbiter Challenger now being moved the final very few feet into position over the support posts. We see the pin at the bottom of the mobile launch platform moving over that support post. The driver of the crawler transporter has only about 2 inches of leeway to position his 14 million pound load. and it has to be done rather precisely so that the mounting pin at the bottom of the mobile launch platform will fit precisely into the launch post and drop straight in when the mobile launch platform is lowered. Maneuvering is very difficult because, of course, the mobile launch platform cannot be moved sideways, so the crawler, transporter, driver has to be very, very careful in lining up all 6 of those pins over the 6 launch posts. When it is in position over the mounting hole, the entire mobile launch platform will be slowly lowered into position. The pin will drop into its socket, and then workers at the top of the launch post will install huge bolts that connect the mobile launch platform to the launch post themselves. It wouldn't seem necessary to bolt down something that weighs 8 million pounds, but the launch stresses are rather severe. The 6.5 million pounds or so of thrust generated by the Space Shuttle produces a lot of vibrations and movements, and the bolts between the post and the mobile launch platform help ensure that the platform itself does not actually bounce out of position during launch.
Okay, thank you. Good morning. As Hugh said, our schedule is to get to a T0 tomorrow morning at 11 o'clock for the first firing of the engines. The primary objective is to check the shuttle vehicle integrity and the performance of the main propulsion system. That includes the orbiter systems, the ET, and the Space Shuttle main engines, the SSMEs. We have some secondary objectives. One is to verify the combination of the launch facility. You know, this is a new mobile launcher. We've not fired off of this on the Space Shuttle before. And we'll test the total system as we fire the engines. We'll establish any baseline that we might need for the future as far as any minor leakage of the hydrogen system in the aft compartment. This baselining is necessary to know whether or not we've got a significant problem on future launches. And we will determine what we call the twang of the vehicle. When the SSMEs ignite, the vehicle has a tendency to tip toward the north, so we'll assure ourselves that the twang response of the stack is as predicted, and that in turn determines when the SSMEs, the SRBs rather, are ignited for launch. But we don't expect to have any change in that timing sequence as a result of the test. And of course, we'll be checking the APUs. They will be fired tomorrow on the orbiter, the auxiliary system there, and we'll check the hydraulics and the flight control systems.
T-minus 1 minute and counting. Firing system that releases the sound suppression water onto the pad has been armed. T-minus 50 seconds and counting. T-minus 45 seconds and counting. T-minus 40 seconds. SRB development flight recorders are being turned on. T-minus 37. Gaseous oxygen vent arm will not be retracted on this particular test. T-minus 31 seconds. We have a go from LPS for auto sequence start. 4 primary flight computers taking over main control of the terminal count. Final LPS command for engine start will occur at approximately T-minus 10 seconds. T-minus 15 seconds and counting. T-minus 10, go for main engine start. Hydrogen burn igniters are, we have engine start on the first main engine. 0, T-minus 0, engines throttled at 100%, all 3 engines up and burning. T+5 seconds, engine continuing to burn. T+10 seconds. 12. First cutoff, T-minus plus 15 seconds, engine cutoff, and engines 2 and 3 also cut off at T+, 16.8 seconds. T+, 25 seconds. GLS safing now in progress. We are continuing to run the APUs. We'll now turn them on to high speed for approximately a minute and a half high speed run. APU high speed is verified, T+, 45 seconds. T+ 1 minute. APUs continuing to run. They'll run for approximately the T+ 2 minute mark. T-minus 15 seconds and counting. T-minus 10.
9, we have a go for main engine start. 6, we have main engine start. All 3 engines are up and running. So 20-second firing. We have approximately 7 more seconds remaining. At 100% thrust. And we have shutdown. We have shutdown on time.
I assure you, every one of us take this absolutely as our final responsibility, that we have 4 lives that are going on that ship. And in addition to that, we have the treasure of the nation and, frankly, the hope of the space program going on every time. If we had any real lingering doubt about that, we wouldn't do it.
This is shuttle launch control at T-minus 3 hours and holding. The astronaut prime crew is presently in the breakfast room and prepared for breakfast. Joining the crew this morning for launch are some of the support astronauts, James Van Hoften and Woody Spring, Anna Fisher, Kathy Sullivan, Sally Wright. At the other table, the Associate Administrator for Space Flight at NASA headquarters. This is shuttle launch control, T-minus 2 hours, 36 minutes, 38 seconds, and counting. The flight crew is just in the process of leaving the crew quarters in the O&C building and is in the elevator ready to go down to the first floor, with the exception of Story Musgrave, who has just run into the elevator and been greeted by Don Peterson, the other mission specialist. John Young among the group, and they're just about to close the door and will be on their way to the ground floor and the Astrovan, which will take them to the pad. They're on their way now out of the door of the O&C building. Commander Paul White's waving to the crew, entering the Astrovan along with the mission specialist. Carol Bobko went over and shook hands with somebody who wished him well on their trip. The van being closed up by the security chief for this particular job, Gene String, and they are on their way to the pad, and a launch on time at 1:30 p.m. Eastern Standard Time this afternoon. Everything going very smoothly in the countdown. The countdown clock at T-minus 2 hours, 24 minutes, 5 seconds, and counting. This is shuttle launch control. The astronaut crew has reached the White Room on the orbiter access arm and are preparing for their entry into the crew compartment. Commander Paul Weitz and Carol Bobko in the process of putting on their harnesses.
Crew leader OTC. Yes, crew, let it go. We have NPD concurrence to proceed when ready with crew ingress. Copy. And OTC from ASP. Station calling OTC. Call again, please. That's ASP. Do you want to go ahead and do the caution and warning memory clear? Clear the caution and warning, please. Better. ISL, stand by to take anything down.
In the process of putting on his Snoopy hat and his launch and entry helmet, which is a hinged helmet that is placed in place and then locked around the neck, makes a seal for the launch and entry to provide both communications and life support functions. In the past, when the spacesuits were used during the launch and re-entry phases, the helmet locked to a ring on the top of the suit, but now a different sort of device is being used.
Everything going smoothly in the countdown. I've had a report from the support astronaut that the switch list of switches inside the orbiter has been configured for entrance of the prime crew into the crew compartment.
And Commander Paul Weitz, or P.J. Weitz, has entered the crew compartment at present in the orbiter, preparing for launch, which we expect to be on time at 1:30 p.m. The countdown going smoothly. The clock at T-minus 2 hours, 13 minutes, 8 seconds, and counting. This is Shuttle Launch Control. The mission specialists for STS-6 are presently in the White Room, getting ready for their entrance into the crew compartment of the Orbiter Challenger. Actually, the harness that the astronauts are wearing is used in case of an emergency, and there are two parts to it. One is an integrated harness and egress sling, which would be used for exiting from the orbiter in the case of an emergency landing. The other portion is called the personal egress air pack and provides oxygen where they would have a contaminated atmosphere. This differs from the harness worn during previous flights because for the first time, operational type seats are available in the orbiter. The Columbia, which we'd flown on the first 5 missions, had been configured with ejection seats for the test program and with temporary seats for the mission specialists. With the Challenger online, we've moved into an operational type seat for the entire onboard crew. Also getting ready for his entrance into the orbiter is Dr. Story Musgrave.
Anything wrong with doing that at this time?
We can verify step 310.
Thank you. Flight control.
Flight control.
311. Would you rather close out crew? Close out crew leader. RTC. Go ahead, crew leader. Okay, MS1 is ingressing. Understand. Seen him on camera. Yeah, flight control. Do you have any problem with doing 311 at this time?
311 is verified.
Thank you.
Mission specialist Don Peterson taking a look inside and is just about to enter the orbiter. The countdown clock at T-minus 2 hours, 7 minutes, and counting. This is Shuttle Launch Control.
OTC, ECL 212.
Go ahead, ECL.
When the crew, close out crew just got a chance, can we talk to him on 143?
All right, don't see why not. Crew leader, are you available to go 143? I copy, we'll do that now. Thank you.
Just close out crew back on 212.
Copy.
Indicating about 151 now.
This is the ascent liftoff for those of you who weren't fortunate enough to be there. Very fortunate from our standpoint, but I understand from the folks on the ground it was one of the clearer days we've ever had in Florida. When the solids get a hold of you right here, you know you're going where those solids want to go, and you hope that something keeps them pointed in the right direction because you're on your way.
Alignment attitude for you should your star tracker, -E star tracker, be failed, and whenever
the
you
roll,
want to
as
copy
reported
that,
before, was not
after Guam, we
disconcerting
can
or
give it to you.
confusing in any way. You know, that's about a 90-degree roll there as soon as you clear the pad.
This is Shuttle Control. Yargity has loss of...
As Bo said, we were kind of prepared for more shaking and clattering and vibration than we actually had.
This is Shuttle Control at 2 hours 41 minutes mission elapsed time. Standing by for acquisition through Guam. This will be a 2.5 minute pass at Guam.
Okay. We're on time, and we can even get ahead if you're ready to copy some very gross estimates of aileron.
We're approaching SRB SEP here.
Roger, we're ready. Go ahead.
You can see tail off. There are the SEP motors, and as I say, those cause it to fall away in the right direction.
They're either a trail or down some degree, some amount like 5 or 10 degrees.
Okay, we copy that, and be advised that I have a second alignment attitude for you as a backup in case you have trouble with the -Z star tracker, and whenever you're ready to copy that, I can pass it to you.
Okay, stand by.
In room 135 at the JSC News Center. Present estimate for the change of shift news conference, 4:05 p.m. Central Standard Time, room 135, JSC News Center. At 2 hours, 46 minutes mission elapsed time, this is Shuttle Control, Houston.
Hello, Challenger, Houston with you, the Crystal team through Hawaii for 8 minutes. Challenger, Houston, Crystal team with you for 7.5 at Hawaii.
Houston, we go.
There you are. We got the Crystal team here with you at Hawaii for about 7 more minutes.
Roger. MS-1's been calling you. Are we go for the IUS sec? Got ready?
We need about another minute. We'll let you know here shortly.
Roger, I understand. 1 minute.
Okay, you got to go for a power transfer, and you got to go for the checkout.
Roger, we understand. Here we go.
And if you could, we'd like a spec 62 and an item 6.
Buckhorn, Comtech, yes, taken.
You're loud and clear also.
Meet me on 2.
Roger.
Buckhorn, Houston, how do you read?
I read you bye-bye.
Stand by for keying and modulation.
Roger.
Houston, 1, 2, 3.
No, sir, we're not configured yet. We'll do that over Mila.
Okay, I've got a camera set up for you to look at the, what looks like some frizzy fuel.
On Shuttle Flight 6, Challenger's cargo, the Tracking and Data Relay Satellite, TDRS, and its solid propellant inertial upper stage rocket, the IUS, weighed almost 19 tons. TDRS was the largest, most advanced communication satellite launched to date.
That is correct.
A major accomplishment in space communications.
Challenger Houston, we're 20 seconds to LOS.
This is a view of the tracking and data relay satellite in the bay.
Entry refs mats are on board. We'll talk with you next to the car at 152.
The car at 152, thank you. We've had the binoculars out for the doors. The total door operation was nominal.
Roger, we copy. Now go ahead and follow nominal procedures. You've got to go for deploy.
We'll pick up the power transfer and deploy minus 20 minutes then.
That is correct, and we'll see you down in Santiago.
clocks.
Okay, it's moving. Boy, a little slow.
It is slow.
Here it comes. It ain't real slow at this end. Oh, it's coming up. Can't look.
God,
Go back
this
down
is
there.
absolutely fantastic.
Go back to
How
your-
long have we waited for this?
Go back to your panel.
No, I don't want the pedal.
The whole world is over at that panel over there. Just stay
The
there.
motion's gray. That's all I need to know. Look at that beauty. This line right here, from the 29
What
gets
line?
to this line. That beam right there.
Okay, we're almost there.
This is as we were elevating it from the stowed position to the 29-degree checkout position. That thing just moved majestically. It is quietly, silently, as a matter of fact, and almost inexorably goes about its thing. This is as it was moving up toward the final attitude. 45 degrees, you can see on our protractor that was our minimum elevation angle. Once it got to 45, if everything else was okay, that thing was going, whether we got to 58 or not. Now that's the nozzle of the solid rocket motor, and this is the instant of separation. As Don said, we really had to kind of check the television view from this aspect to see that it was in fact deployed. Absolutely perfect deployment mechanically. It came straight out of the ASE, the Airborne Support Equipment, with no rates, just at, again, at its 0.4 of a foot a second, which isn't all that fast. And now at about a minute after deploy, as we thrust backward toward it, and you're not sure the thing is really clear of the orbiter, but that does cause you to pitch down also or away from the thing. But nevertheless, it gets its attention when you're thrusting back toward a 17 or 18 ton piece of metal in the sky. The white part is the IUS, the inertial upper stage. Here's where we started to thrust toward it and pitch down.
Hello there, we're with you over.
Launch of TDRS was on time and nominal.
And a reminder not to do the secondary check on that left, Holmes.
Yes, sir, we won't do that. It was a good deploy, John.
That sounds great.
First stage firing of the inertial upper stage also went well.
And Sunnyvale and White Sands send you a special attaboy.
However, halfway through the second stage firing, ground controllers lost communication with the satellite. It was an hour before even intermittent signals were picked up. They indicated TDRS had not yet separated from the IUS, and that both were tumbling at a very high rate of speed. Receiving only intermittent signals from TDRS, using short-life batteries which would soon be depleted, and getting no response to signals sent from the ground, made the outlook for TDRS bleak. Several more hours passed, and then something remarkable happened. Experts still aren't sure why, but either an automatic timing mechanism was engaged, or onboard systems finally acknowledged repeated commands from the ground, separating TDRS from the IUS.
Well, I do have some words.
Now on its own, the satellite stopped tumbling. Ground controllers commanded deployment of the solar array and antennas. However, they quickly learned TDRS was way off course and drifting farther every day. Their only hope of getting it back on course was to use the tiny hydrazine thrusters originally designed for minor attitude and velocity adjustments, not for boosting the 2.5-ton TDRS over 8,500 miles farther into space. But at least the satellite was not lost. NASA officials immediately put their plan into effect.
Mount the camera up here and adjust the f-stop to get about a speed of the 60th.
That is Story operating the camera to take data for the continuous flow electrophoresis system experiment. This is a joint venture between McDonnell Douglas and Johnson & Johnson, which they have every confidence is going to have direct earthborne application very shortly.
What we're doing is injecting samples at the bottom down here, electrical field across the column here separates these particles out according to their charge from a neutral point right here on out in this direction here. Okay, here's some of the other kinds of things that we do here.
He was taking some photos of the streams up there and down here. He's getting ready to change out some samples.
We enter the sample right in here. The sample is injected down here in different ports here. It's carried up with a carrier there. There's 200 exit ports up here in which we insert a tray in there and collect the sample in 200 different compartments, depending upon the separation achieved along here. You can't see it around the corner here, but the experiment control module is here. The generator we use to store the samples is right here. Of course, for running the electrophoresis experiment is on there. Here's the light we use to take the pictures.
As you can tell, Brian, this is looking at the port side, and he's just going to scan on across there. But you know, this is the office. This is where we do our business, and that's what we got it set up to do. Well, looks real ship shape. Well, we try to keep it neat. We've got a picture of the CDR, but no sound. Forgot to test it. I say a little warm coffee here. It's always 6 hours. I tell you, in this environment here, the coffee sure cools off in a hurry. Roger that.
Brian, I got some more numbers for you.
Roger, ready to copy.
Delta P1 is 10.5, 2 is 10.7, 3 is 5.8.
Okay, Story, and we have 50 seconds to go on this pass.
And this was flight day 2 here, while Bo was telling the world about the getaway specials. They were mounted in those 3 canisters.
In any case, I'm just about ready to get the gas canister from the Air Force Academy going here. I was going to take a look at it with a TV picture, the TV camera that's outside, the one that's just on the other side of the bulkhead here, and I'll give you a look as well.
Sounds good.
What you see now, of course, is where we launched the TDRS and IUS from yesterday, and the gas canister is on the right-hand side. And I'll bring the picture over so that you can see those gas canisters. There are 3 of them. There is the Japanese gas canister, which is investigating the production of snowflakes in orbit. And then the Park Seed Company canister, which is going to be looking at the space environment's effect on seeds. The middle one is from the Air Force Academy. And that has a half a dozen different experiments on it. There's a metal beam joiner, where they're going to try to join metals in space, a miscible alloy, a foam metal, a crystal purification, a microorganism development, and an electroplating experiment. Okay, this is a little encoder, which is used to turn on the gas experiments. It's a common encoder, and it's used for all of the gas experiments, but there's a code which is used to address each. The Air Force Academy experiment has 2 relays in it, and I'll call up the first and turn it on. It shows now that it's latent, and I'm going to turn it over to hot.
Don't make any mistakes.
And 00 does show that it's hot now, so it should be running. And 01 from latent to hot, so it should be running at this time as well.
Okay, we copy.
Looks like those gas canisters are, in fact, going to be running. I hope they get good results from them. I think it's a great opportunity for a lot of people, and especially for students, to be able to look at the environment of space and see how it affects all sorts of different items. Nozzle is a rather simple experiment. It's an experiment to take photographs of thunderstorms and lightning from the advantage we have here in space. And what it consists of is a detector which will detect the electrical and light activity, and just a normal 16-millimeter camera that has been used on many aircraft programs before. When we go over places like Central Africa or South America where there are likely to be thunderstorms at this time of the year, we point the picture at the thunderstorms and point the cameras and take pictures. We also have associated with this recorder so that we can record our comments. People are very interested in this because they can see how lightning propagates from one thunderstorm to another, or may encompass a whole area, something that's very difficult to appreciate from the ground or even from a high-flying aircraft.
There we go. Now, we go over here, check the table. Well, they should be all 20s and 2s, Bo. Right. Except for a 200 that's thrown in here every now and then. Plus, the glide slope bug is off, just like it is in a simulator.
This is the FCS Flight Control System checkout. We do it every flight on the vehicle.
Well, we'll let the ground call it. When you want to go down to see Dawn in the middeck with the CFES, Houston? Am I? You just give us a call when you want us to switch, Roy. My GSI is more than a tick down, Bo. Glide slope indicator. Houston, we're ready for a switch to the middeck. Okay, coming at you. Okay, what I'm doing right now is getting close down to taking a photo here, about 4 minutes away, to photograph the entrance of sample 5 into the flow column in the sea.
Don was basically, he was the housekeeper, and you can see that he kept a nice, neat ship down here. You know, there's not a lot of trash and equipment and items hanging on the lockers and on the bulkhead. And we did a antenna test which necessitated us getting crossways to our velocity vector and then rolling at 2 degrees a second. We took some pictures of it, and I tell you, it was a little more impressive from on board than it is here. But nevertheless, it was a welcome diversion from just going around the world with a payload bay facing the Earth all the time.
Yes, am I talking to the Space Shuttle Challenger?
Yes, sir, you certainly are.
Well, the American people are very proud of your service to your country and what you're doing. And we wish you well on the continued flight and on the spacewalk.
Well, thank you very much, sir. It's an honor and a privilege to be here, and we very much appreciate your call.
All right, goodbye.
So long.
The first spacewalk, or extravehicular activity, in connection with a shuttle mission took place on the 4th and 5th days of the flight, as mission specialists Story Musgrave and Donald Peterson became the first American astronauts in 9 years to walk in space.
That's Story and Don in the airlock, beginning their pre-breathe. You know, requires 3.5 hours of pre-breathe on 100% oxygen to make sure, or to have better assurances that we've flushed nitrogen out of the system so folks don't get the bends when they're exposed to the lower pressures in the suit. Bo was cleaning up the airlock and making sure that everything was ready for him.
Okay, it's 12 frames per second. Speed is 1/60th.
This photo was taken through this is from the aft TV cameras. That's the airlock hatch being opened in preparation for airlock egress.
Need to use the spot meter also.
Okay, Don's out of the hatch. Story's up to the starboard longeron. I looked up and saw him looking over my shoulder in here.
This was America's first spacewalk in 9 years. The astronauts were attached by safety tethers to slide wires running just inside the payload bay.
And this is a story like a butterfly coming out of its chrysalis.
They wore a new design in spacesuits, also called extravehicular mobility units. A portable life support system was worn on the back, eliminating the need for a lifeline connected to the orbiter. These suits are not custom built for each astronaut. Tops and bottoms of different sizes can be mixed. They are also more flexible than previous spacesuits. The crew removed tools from a storage locker in the front part of the payload bay.
I'll discuss the extravehicular activity, or the spacewalk. The thing we wanted to test and evaluate there was our ability to do construction type work, repair type work in the environment of the shuttle orbiter. We wanted to check out our suits and the life support systems on the back that we call EMUs. We wanted to evaluate how we check them out before we take them into the airlock and depress and take them outside. We did have 3 suits on board. We wanted to look at our ability to move about in the payload bay, up and down the longerons, or up and down the long distance of the payload bay, and across the bulkheads fore and aft. We wanted to look at our safety tether dynamics, the safety tether we wear to be sure that we stay connected to the orbiter. We wanted to exercise various tools, winches, and in summary, our basic ability to do work, constructive type work or repair type work in the environment of the orbiter.
How's that compare to the water tank story?
Well, it's all viscosity. But you get it going, you keep it going. That's a reach right there that I can make. Water tank that I can't make either.
Musgrave now at the aft bulkhead, evaluating the handholds on that rear wall of the spacecraft cargo bay.
Got a good shot of Mother Earth behind you there, Story.
I've been used to working in.
Musgrave comparing the spacewalk to his earthly training in the water tank, saying it's a little deeper pool than he's used to working in.
We're looking right at you, Story, with camera Bravo.
I see you. I'm going to sneak down around you so I can watch Sean. Okay, Don? Patricia? Why don't you head on across the port side? Maybe down here. Okay, I'm going across the bottom.
Peterson now moving along the port slide wire, cargo bay, beginning to lose signal now from the tracking station at Hawaii.
How's the crew back here? There's loads of lights.
we've been through the usual fixes.
Story, is the winch rope attached to the IUS at this time?
Yeah, it is.
You can't get any slack in that line at all, huh, Story?
That's right, not enough to get off the hook. Now, the good possibility is if I can get it off the roller up above, I'll get some slack that way. Okay, I got it. I yanked it off the roller. Now, before we do anything else, if it ain't gonna release, we'll get the snatch block undone. We'll know we're home free.
Not until you lift it over that hook.
Using a cable run through a winch mounted on the bulkhead, then tied to the cradle that had held the IUS, the astronauts demonstrated they could have lowered the cradle manually had commands from onboard failed.
Don here is back at the IUS tilt table. This is in the aft end. He's using a ratchet wrench here to reposition some equipment. The story mentioned before, their practice run-through of the IUS tilt table restow mechanism for which we have an EVA procedure.
I'm getting the winch to winch out. We've been through it before with tension on it. Cannot get it to ratchet out, and we cannot get it to reel out.
We copy.
Okay, now we're going to see what the safety wire would do to me if I ever got loose. What it would do right here.
About 3 more, Bob.
It's just kind of a gee whiz thing. I tell you, this thing really does have a Star Wars effect. 65 feet is a long way back, and it's a big vehicle, and it's still surprising. You look back, you're in orbit, you're in a spacecraft, and the damn thing has got wings and a tail. It seems innocuous. And when those guys were in the back end of the vehicle, they were far enough away, and everything just absolutely silent. You know, you're gliding over the Earth due to some fortunate magic, and they're back there having a heck of a good time in this case, and it really does have, it's more Star Warsy than Star Wars, I think. Except Star Wars spaceships have wings also.
It's a fantastic view.
This is, as we were going down, we're fortunate here. That's the west coast of Mexico, just below Guadalajara, where it kind of bends from the southeast to the east-southeast. So we were zinging right along the Mexican coast, which has no significance, except I think it makes for a nicer-looking picture than if you had nothing down there. You notice on the fin, the rudder is offset to the left a little bit up there. That kind of surprised me. It turns out, in talking to folks afterward, that the flight control system checkout leaves the rudder parked to the left, and it's nothing to be concerned about. That's just what it does. The helmet-mounted lights were, for all practical purposes, essential, and at the payload bay, floodlighting was not adequate to do your tasks.
Winch operations were tested on the front bulkhead using an Exergenie as a load to see how many pounds the winch and line could handle.
Story here is using the EVA winch that is utilized for several different tasks. This is on the forward bulkhead, and it's routed down to, he just pointed to an Exergenie down there, which is used only to provide a load on the line that we use.
There you go.
go now?
Okay.
I think you can make it now, probably.
Here we're doing some suit mobility checks, kind of reach envelope determination, suit stability and mobility evaluation, seeing if there were any objectionable lockups in any of the bearings. See if you could put it in one position where you wanted it, keep it there, so-called neutral point. Performance of the EMUs was just like the performance of the vehicle. It was, we've had some bad starts, but they both work like champs in this particular evolution. And we're very gratified by that also.
Lastly, the tools were restowed, and the astronauts re-entered the spacecraft.
Okay, guys, what do we got left to do out here? Bay looks clean.
I believe we've done it, Story.
Musgrave's completed closing up the toolbox. Peterson is in the airlock.
This is getting back into the airlock. Turns out we have a little work to do on the term Story used is choreographing this evolution, and that's a very good term, I think. Is that as far as our procedures for getting out of and into the airlock.
Thus completing the shuttle spacewalk, first one of the Space Shuttle program. It's a walk that lasted nearly 4 hours. Crew had plenty of margin left in their consumables, the power and the oxygen, all the life support systems in their backpacks, and had completed all the tasks outlined for them in the EVA checklist, and are now back in the airlock. At 3 days, 6 hours, 26 minutes mission elapsed time. This is Mission Control, Houston.
This is on the last day of the flight when we had our impromptu conversation with the Vice President.
This project has been brought to you by the Jericho Bunch.
And we decided, we were notified during the flight that we had the dubious distinction of being in average age, the oldest crew to ever fly, anytime, anywhere.
Okay, we're very pleased to find this stashed somewhere in the vehicle. And it just goes to bring home that old adage, is that space whiz John Young has said that space flight is really for old folks. And, well...
That's great.
And maybe that's why we try a little harder.
Turn it down just a little to get the glare off of it. There. 111 years of aviation experience. All right.
Well, we try to please. Coming in loud and clear.
Well, I just wanted, this Vice President, and I just wanted to say we're sitting here. Don't panic. There are other Capcoms sitting next to me, but I just wanted to add my words of congratulations to those of my boss yesterday. Say how much we appreciate what you're doing. Over.
And we see Palmy Lake Edwards being the sun below us here.
Sir, probably a lot of sailboats out there today.
After 5 days, 80 orbits, and 2.2 million miles in space, Challenger completed its maiden voyage with a perfect landing near the Mojave Desert in California, April 9th.
Okay, verify you're still at the close aim point.
That's a firm.
14,000 feet altitude. Still in manual mode on pitch and yaw. 7 miles to touchdown.
This is through the HUD, through the head-up display. The HUD was a tremendous asset. I feel, toward making what subjectively from the operator's point of view, that I thought was a relatively smooth approach and landing. These were taken from the TV photo chase on return to Edwards. You can see the weather was as good out there for entry as it was in Florida for the launch. Here we are in a flare. Preparation for landing. This almost counts as a carrier landing, as you'll see in the next photo, by an overwater approach here.
Edward dry lake bed.
Right. We felt a little turbulence, one gust on the final approach, and it just sailed right through it with no crew response necessary. The touchdown was nominal. From my standpoint anyway, relatively smooth. I didn't hear any gasps, so you guys might all have been holding your breath or something. Speed brakes are starting open. Our standard procedure, as soon as the main gear on deck, I call speed brakes open, and Bo manually opens the speed brakes to help impart some drag.
The unofficial touchdown time at 5 days, 0 hours, 23 minutes, 40.
But anyway, it's starting to come together, folks. The whole system is... we're on our way. Did feel good to be back on the ground again, even though it was a tremendously exhilarating experience, but that is just such a huge, impressive vehicle, especially when it's sitting on the ground.
Wheel stop at 32 past the minute. Challenger's crew now exiting the spacecraft, coming down the stairs for perhaps a walk around, kick the tires before going over to the medical exam and the ceremony thereafter. Being greeted by JSC Director of Flight Operations George Abbey. Here in Mission Control, the mission plaque is being hung on the sidewall to join others from previous programs and shuttle missions, going all the way back to Gemini 4 in 1965.
I cannot say from my own personal standpoint how pleased I was with the performance of this vehicle. And I just can't say too much about this vehicle, which demonstrates to me the maturity of the entire shuttle program, the shuttle transportation system.
Challenger is now prepared for its second flight, Shuttle Mission 7, with launch scheduled for June 18th.